Sure.
Hello, everyone. Okay, we'll just have a few more coming in, and we'll close the door. Excellent. So we'll now kickstart the next talk. Let me first, before we begin, allow me to introduce Mr. Peter Silberman. Peter Silberman is an engineer.
Thank you.
Before he even presents, wow, that's a vote of confidence there. He's an engineer from Mandiant Inc. He works at Mandiant as an engineer on the agent team, and for a number of years now, Peter has specialized in offensive and defensive kernel technologies, reverse engineering, and vulnerability discovery. He enjoys automating solutions to problems both in the domain of reverse engineering and rootkit analysis. Peter now spends most of his time researching solutions to memory forensics problems. Peter is the co-author and teacher of Advanced Memory Forensics in Incident Response. And although he is college educated, Peter does not believe formal education should interfere with learning. Today he's going to be presenting full process reconstitution from memory, and do join me in welcoming Mr. Peter Silberman.
Thank you. Thank you. All right, so as she said, I'm just going to rehash things because my slides are set up that way. I'm here to talk to you today about full process reconstitution from memory. What that means, well, first, what I'm going to do is I'm going to tell you a little about myself, cover a couple things real quick, won't bore you. Then I'm going to talk to you about acquiring physical memory, because before we can do full process reconstitution, we need access to physical memory, and we'll discuss the different methods there. We'll do a little deep diving on the software physical memory acquisition. We'll then talk about traditional process acquisition, what that means, what we define it as, what you may think of it as. We'll discuss some of the pros and cons with regard to that. Then we'll go to the new process acquisition approach, the one that we'll be releasing here at Hack in the Box, the one that will be included in the tool, and the one that we'll continue to talk about throughout the slides. Once we talk about process acquisition, you guys have a good understanding of it. We're going to talk to you about some of the really advanced things we can do after we've acquired a full process. Once we've done that, that would be the find executable code bullet you see there. Then we're going to talk to you about Memorize, which is the free tool that we're releasing here at Hack in the Box. I couldn't travel across the world with 300 CDs. It really was pretty unfeasible. So there are cards. I have cards with the URL. They're in front, so grab them at any point so you guys can download the tool. And hopefully I can get about 20 minutes of demoing just different things in, since I think that would be the most fun. So who am I? Real quick. We already covered what I do. I've co-written 2 projects, RAID, which stands for Rootkit Analysis, Identification, and Elimination. And I'm also co-author of FU2, the second version of FU. I contribute to Uninformed Journal, and I do security research on the side. So before we get going, we got to talk about our stated goal. What is full process reconstitution? It's sort of a new term that we sort of coined here. Basically, it's when you acquire a process, you don't want just the executable. You want to dump all the executables from memory. That's the DLLs the process has loaded, the executable in the process address space, and on top of that, you want process-centric information. So I'm going to want the stacks for the threads that are executing. I'm going to want the heap information. I want to want that all on disk so I can look at it and use it how I might please in either malware analysis or memory forensics. So that's what full process reconstitution is. All right, so what is required? Well, there are a couple things that are required. We need access to physical memory. We either need access via live physical access, or we need a memory dump that was created, and we can treat that as physical memory. After we have access to physical memory, either via a memory dump or live physical memory, I need the ability to find all the processes on a system, whether they're hidden or unhidden. Once we've found every process, that means we can find the process that we want to acquire from. Once we can do that, we need to be able to parse that process's memory sections. And we'll talk about what parsing memory sections means and what it is in a couple more slides. So that's what's required for full process reconstitution. So there are 2 different ways to acquire physical memory. The first genre, if you will, is hardware physical memory acquisition. And that's going to be your PCI and your FireWire. PCI, Joe Grand of Grand Idea Studios came up with a hardware device called Tribble. It's a PCI card. You stick it in. It'll suck the physical memory off the machine, store it for later analysis. The second method, FireWire, was developed by a couple people. There was the first group was a CanSec West 05. They gave a presentation. Their method wasn't as solid as they would have liked. They were only really able to acquire physical memory off of XP Service Pack 2, I believe. The second guy is Adam Boulot, who did I think I'm pronouncing his last name right. I may not be. He did a paper called Hit by a Bus. And basically he was able to trick Windows into thinking his laptop was an iPod device. And he was able to suck physical memory off of the computer he connected to via FireWire. And so those are the two host-based physical memory acquisition, or two hardware-based physical memory acquisition techniques that can be used. But what we're concerned about and what we'll be discussing here today is the software method. So we want to acquire physical memory via software. And to do this, we're going to open a handle to the device physical memory. Device physical memory is a section object that's been exposed by Windows to allow access to physical memory. And this is how we can get live access to physical memory. Next, we're going to want to read from this handle that we've gotten to read physical memory. But we don't know where we're reading. So what we have to do is we take the virtual address that we want to read from. We're going to do a translation, because we need to translate that virtual address to a physical address and then seek within this section object to that location and then read the physical memory that corresponds with that virtual address. So I know that's a lot to digest. So basically, virtual addresses, we parse them in two ways. If the system has page addressing extension enabled, which is PAE for short, we're going to parse the first 2 bits of the virtual address. That's going to represent the page directory page table. The next 9 is going to be the page directory entry. The 9 after that is going to be the page table entry. And then the last 12 is going to be the physical offset in memory. And we do this, and then we seek around in the section object to get to the location of physical memory where this virtual address's buffer is stored. If page PAE is disabled, we're going to go about it a little differently. The first 10 bits are going to be the page directory entry. The next 10 are going to be the page table entry. And the last 12 is going to be the physical offset in memory. So it's just 2 different ways. Basically, Memorize, the tool, acts as its own MMU to translate virtual addresses, and that's how we're able to use utilizing paging file and things like that. So we've translated the virtual address to a corresponding physical memory page, and we've mapped that page into our own buffer that we now control. We have 2 options once we've done that. The first, if we're in live memory analysis mode where we're like scanning for processes, we want to dump the handles a process has, we want to do something in live memory, we're going to scan that buffer for certain signatures or certain characteristics that we're looking for depending on what has been enabled and what has been asked of us by the user. If we're being asked to write the physical memory, if we're being asked to essentially say, create a memory dump, put it on disk, and we'll use it later, we'll just write this page to disk and keep reading in a loop. So those are the 2 different types of what we may do with the buffer once we have it. One caveat that we have to address is that user mode access is not allowed at the beginning, is not allowed to this section object from Windows 2000 Service Pack 1 and on. So we can't, in user mode, open a handle to this section object, which creates a problem because we pride ourselves on being able to support Windows 2000 to Windows 2000 Service Pack 4 to Windows 2003. So we had to come up with a way around this. And this is true in Vista as well. So our solution, I'm going to actually use an animation here since those are more fun. What we do is we run our tool Memorize. Once we've run it, Memorize will install a driver. This driver is now in kernel mode, running in ring 0, so it has permissions to open this section object. Memorize is going to request a handle to device physical memory from the driver. So the driver is going to open this device up in kernel land. Once it's opened the device up, open the device getting a handle back, it's going to pass that handle back to user land. So we now have the handle that we couldn't get in user land using a driver. It's a technique that's being used by a couple other tools we'll talk to you about in a second. So once we have this handle in user land, we can now read physical memory in user land, which is our goal. So let's say Memorize wants to read the virtual address you see on the screen. What would happen is Memorize would translate that virtual address to the physical address, read that buffer from device physical memory, store the buffer, and we're going to say for this instance that we are actually in memory dumping mode. So we're going to write that buffer to disk. Once we've done that, we loop, and that's how we create a memory dump. We don't repeat the process of requesting the handle. Once we have the handle, we do that once. So the translation is what occurs in the loop. So that's how Memorize does memory acquisition. We are not unique in this aspect. There's 3 other freely available tools out there. MDD is open source, and Win32DD are both open source memory acquisition tools. They only do memory acquisition. A quick note, Win32DD was written by Matt Suchet. He is, if any of you are familiar with the hibernation file, he wrote the Sandman project. So that's a good website to have in mind. He does a lot of cool stuff in Python with parsing things. So that's a good place to go. And then we also do it. But Memorize, which stands for Memory and Analyze put together, does it a little differently. Win32DD and MDD rely on system calls. System calls can be subverted. As we all know, rootkits from way back when can subvert system calls. The system calls that Win32 and MDD rely on are MDD relies on global memory status EX, and Win32DD relies on ZW query system information. Both of these calls, what they'll end up doing is returning the actual physical size of memory that these programs should create. The subversion can occur where you can hook these API calls and return a smaller physical memory size set. And what that means is that you're able to say, don't acquire up here. My driver may be in this location. I don't really want you up this way. So I'm just going to give you a smaller set. If memory should be 512, let's divide it in half and say 256 is the actual physical memory size. This is a theoretical rootkit approach. As far as I know, it's not been implemented, but it wouldn't be hard. One thing we'll say is that the API calls that MDD and Win32DD call are not really unique. Or actually, I apologize, they are unique, that they're not called by many processes. Memorize does not rely on these API calls. What Memorize does is it relies upon an API call that is very common to us, map view of file. Most of us should know about it. It's used by most processes. Most applications will have this call somewhere. It's just a common way to read a file. We only use this to determine the size of physical memory because we'll actually get an error once we read past the end. So we don't need to predetermine the physical memory size. Map view of file, we are aware, can be subverted. How an attacker would go about doing this is they would have to know their driver's physical address, where their driver is in physical memory. So they'd have to take the virtual addresses that their drivers are on, translate that to physical memory, and then block reads to that physical memory. We believe that's a lot harder to do. 1, because they'd have to implement their own translation, which is not easy. And 2, because physical memory is not contiguous. So an attacker may make the mistake of saying, well, I got the first virtual address, I got the first physical memory page I'm on. I'm just going to add to that and say that my driver is going to be here. Well, we know that virtual addresses don't map to contiguous physical memory pages. So that makes it that much harder. So we try to minimize the possible subversion. So that's some of the software drawbacks. So let's talk about traditional process acquisition. Because basically, what we're saying is that we're coming up with a new approach. So what is the traditional approach that we're trying to avoid? And the traditional approach is not a bad approach. It serves a lot of purposes. I still use it personally, even with the ability to do new process acquisition. This is essentially, the old approach is acquiring an executable from memory. And why you want to do this is basically you have a file on disk. Let's say it's packed with UPX, which is pretty common. It doesn't look nice on disk. It doesn't look nice in IDA just because it's packed. But we know it's going to completely unpack itself in memory. So doing a traditional process acquisition is going to give us a view of the file that we don't have on disk and make our lives as a reverse engineer or a malware analyst a lot easier. We're going to see strings we didn't see before. We may see API calls we didn't see before. It's just a nice view. And we also know that if it's in memory, that's what's actually executing. So that's a good thing to think about. You don't know what it's doing on disk, but if it's in memory, you get a snapshot of it. You know what it's doing. The traditional process acquisition that we'll refer to from here on out really is going to be an ollie debug type process acquisition where we use ollie dump just to attach. Ollie dump does a lot of really cool stuff that we're going to talk about in a second. All right. So there are many pros to traditional process acquisition. The biggest and best pro that we really find makes traditional process acquisition useful and stay around is that ollie dump and other tools out there will perform the section and import address table fix-ups for you. They automate that. They build the IAT. It's a beautiful thing. It's very nice. It helps with analysis later on. We don't do that. Memorize will not fix anything up for you. And we'll explain why and give you some real-world examples of why we don't do that and what you can miss by doing actual fix-ups. But there are some cons to traditional process acquisition, which is sort of what led us to be where we are right now. The first is you're only getting the binary you attach to. Now, in ollie dump, you can configure it to dump more of the range, but you're not getting it separated out in a file. It's not unique. It's, put in one place. So you're really only getting the binary attached to, which may, if you're looking at, for example, a process that you think has been injected, getting the binary is not what you're curious about. You actually want that DLL that may have been injected. So you're missing something with traditional process acquisition. Also, the other thing that you're going to run into is detection of detecting your, there's a monster. Detecting that you're being debugged right now is quite easy. I put a link up there, OpenRCE. It is actually just a reference library of where you can different methods to determine your process is being debugged. And if you can preventing debug can prevent process acquisition, and that is a fail point. That is unacceptable. It's too easy to do process debugging detection. So that is another reason why we're going to build up this new solution. So this new approach, I'm going to break it down to you how we implemented it. You're going to get all the information. Remember I said that the first requirement was access to live physical memory or access to physical memory. So we've covered that. We told you that we go to the software method, device, physical memory, object. We've got that covered. The next thing we need to do is find all the processes in memory. Because the way we work is we ask the user, what process do you want to acquire? And then we have to go find that process. So if FU2 is running on the system, then we got to find that process, even if it's being hidden. So basically, processes are represented by eProcess blocks in the kernel. So every process has a corresponding eProcess block. This is an unchangeable feature. If the process doesn't have an eProcess block, the Windows manager isn't going to know about it. It's not going to necessarily get scheduled CPU time. It's going to be a big problem, and you may just see your machine blue screening. So it's pretty safe to say that every process has an eProcess block. With that said, we know that there are certain characteristics of the eProcess block that can't be changed. By changing them, Windows may kill the process. Windows may stop the process from executing. It may still be in memory. You may still see it in your task manager. One example was, but it was not getting any CPU time, so it's not actually executing. So changes to certain characteristics of the eProcess block will hurt the process that you're trying to hide. So we look for those characteristics that can't be hid, and we do this by scanning every memory page. When we map that memory page, we look for these characteristics. And using this method of scanning, we're able to determine all the processes running on the system, hidden or unhidden. With that said, we have a caveat. The method's good. It's a little too good, and Windows doesn't do a good job cleaning up after itself. We've found processes after reboot, dead processes after reboot. You're not guaranteed that the process you found is still running. So you need a good method to eliminate processes that have been exited, and you have a high number of false positives in memory. The characteristics I talked about are not big enough to eliminate all of memory. So you'll find the characteristics in dead memory, in garbage memory, uninitialized memory may look like an eProcess block. So you need a good method to eliminate those as well. I'm not going to dive into the actual characteristic elimination, things like that. That's all public knowledge. If you just Google it, I want to stay with the scope of this and try to get the demos in. But there's a link to one paper we gave about process detection that went a little more in depth than I did. Basically, we now have an ability, using this knowledge, to find all the processes on the system. Every process address space needs to be managed by Windows, because what happens is Windows is going to load DLLs, executables in your virtual address space. And it needs to know what's available. So if you execute a new thread, that thread's going to need a new stack. And that stack, Windows is going to have to know where to put that stack in your virtual address range. And it doesn't use contiguous addresses. So basically, Windows might put your main executable at 4000, and then might put a DLL at 77 something, and then might put a stack at 001C, and it needs to know what else is available for it to use. So the memory sections are just blocks of memory that Windows knows about. So we need to, when I said what the requirements were, we said physical memory, access to physical memory, determining all the processes, and then being able to find all the memory sections the process owns. So Windows does a really good job managing all these sections, and what that means is we can do a really good job doing full process reconstruction, because we can just pretend like we can parse the management it's doing. So what we have here is every eProcess has a VAD root. So we're going to scan for our eProcess blocks, we're going to find the eProcess we want to acquire, and we're going to go to the VAD root. The VAD root is a pointer to a tree. This is a self-balancing binary tree. This tree contains what the structure is actually called in the kernel MMVAD, which stands for Memory Manager Virtual Address Descriptor. This tree contains a self-balancing entries of these. If we parse, well, first off, each of these MMVAD structures contains information we need. It's going to contain the virtual start address, the size of the memory section, It's also going to contain things like flags about the memory sections. Once for every memory section we parse, we write that to disk as a separate file. So you're going to have your stacks, your heaps all written to disk in separate files, which is very easy to use. You're going to have your memory sections that contain DLLs and executables named, and we'll talk about that in a second. So basically, just to rehash, you find all the processes, you find the process you want to acquire, you then parse the VAD root, which is a self-balancing tree that contains Windows memory management information that we can then use for our own good. All right, so the VAD structure looks like this. And then the ones in bold are the ones I'm going to talk about. The starting VPN is the starting virtual address of that memory section. The ending VPN is not the ending virtual address. It is the size of the memory section. Parent is the parent pointer in the tree. Left and right are their children. Pretty basic. U is the flag, so we can bit mask out and figure out, okay, this memory section is execute write, execute read write, execute write copy. We can determine all that. The control area is a pointer to a structure that actually contains the name of the memory section. So if SVC host is the process we're acquiring, its memory section, the memory section that contains the svc host.exe executable is actually going to have the name svc host with its full path, which is very useful information and allows us to give the end user very useful information about what was acquired. So just to help, because this may be a newer concept, basically I attached to calc.exe with the ollie debug, and then I did alt-m, which is the memory map view. Is it possible to see this? Every address, it's a little small, I think, but every line in there is a different memory section. So the first address you see is 10,000 hex. That's one memory section entry. It's one entry in the VAD root tree. The next is 20,000 hex, 30,000 hex, and then you see 7B. So you see the addresses between there are unused, and Windows is able to know that and then use that information. So that's why it needs to keep track. It needs to know, all right, I can put a thread stack there. I can do something. If they load a library, I can stick it in there. I can relocate it. So that's all very important information. A common question we got when we first started throwing this around is it safe to assume that the attacker has not modified the VAD tree? And yes, it is relatively safe to assume that. We actually tried to write our own rootkit to remove a VAD entry we want hidden. So like, let's say you inject a DLL and you have a rootkit running as well. That rootkit's going to remove the injected DLL's memory section so Windows doesn't know about it. That blue screens the box pretty guaranteed pretty much, because what happens is it's a self-balancing tree. It's missing an entry. It tries to balance itself out, and it just completely chokes. And rightfully so. There are other modifications that could be made to make it a little harder. In tests, the integrity checking of the VAD root is actually quite good by Windows, and is helpful in ensuring that you're getting what you think you're getting. And I've got a link there to an open source VAD parser. The VAD parsing is not a new thing. We didn't develop it. There's an open source Python script that is able to parse out of memory dumps VADs. So that's the new approach that we have. But there's one caveat that we like to be checked for. And basically, if the memory section is a stack or a heap, it's not going to have a PE header in it. So what we're going to do is we're essentially just going to, the way it works is we say virtual address start, virtual address end, dump it all to disk. If for some reason we can't map some virtual address, it's paged to disk and it's backed by itself, or we're parsing a memory dump and it was paged out at the time, we just write 496 bytes of no ops or 90s. And that way we keep the file size aligned and we keep everything aligned. So if you were going to incorporate disassembly with some reference on the heap, you can use IDA to do that, and everything's aligned so your offsets are right. But if the memory section is a PE file, we're going to treat it a little bit differently. We don't do section fix-up. We refuse to because of a story I'll tell you in a couple slides. But what we will do is we'll take the same dump. We'll start from the beginning and the end, but we make one modification before we make that dump. Or we make a couple modifications. We go through each section header. For every pointer to raw data and size of raw data, we set those equal to the virtual address and the virtual size after we've page aligned the virtual size like the Windows loader. So we modify what those PE headers point to, and that helps IDA, because what we were seeing was we dump a binary, but it was page aligned, so it was a lot larger than it was on disk. IDA would rightly look at the relative offset, and it would see a bunch of 90 or a bunch of zeros at the time, and it would try to disassemble that. Sometimes it would succeed, sometimes it would have some troubles, so we help it along by fixing up the pointers. And like I said, this allows us to stick and idle a lot easier and makes things a little easier for us. So that's the change. That's the only change we make. We don't do any section fix-ups, things like that. We just change what the pointers point to so that they're easier to see because the binary is page aligned. Now I'm just going to talk to you real quick about the Windows PE loader. Basically, what we need to understand is that when an executable is loaded into memory, it's page aligned. So if you have a file on disk, the first 124 bytes or hex 400, and we're talking non-packed, non-themited, non-anything binary, just your calc.exe, is going to be the PE header, usually. What this means is that with page alignment, on disk, you'd go to offset hex 400, and the text section would start. The text section would start. But with page alignment, what happens is Windows loads the PE header at, for example, the base of 01000, and then it loads the text section starting at 01001000 instead of loading it at 10004000. And this is page alignment, memory alignment sort of work. One interesting characteristic we found is that the Windows loader is ignoring the size of raw data field. So it's actually going to say, well, there shouldn't be anything after here. I need to page align it, so I'm just going to load it into memory. And the loader page aligns all that stuff. A problem that we ran into is that if process acquisitions were to rely on the size of raw data for each section, it could potentially miss maliciously inserted data. So we don't, and we actually we mimic the Windows loader in how we align the virtual sizes to make sure we get everything in memory. So I told you I had a story for you. This is from a high-profile target, some malware we found. So basically what these authors did, which was a pretty unique solution, they said, we're not going to write a registry key. We're going to find a system process that's guaranteed to boot up, for example, your SVC host, your services. We're going to then look at a DLL that it imports. We're going to find a DLL entry point that we can modify. So they found a DLL that they thought they could modify. They then overwrote 8 bytes of the DLL. These 8 bytes they overwrote a call with another call. What they did was after they overwrote the call, they inserted malicious code after the relative section size. So after the size of the section, they put their malicious code. When the DLL was loaded in memory, because it ignored the raw size of raw data, the section size, it loaded this malicious code into memory. The call succeeded. The malicious code that they inserted actually loaded another DLL. This DLL had the backdoor functionality that was needed for the attacker to keep control of the system. And that is how they stayed persistent. No registry keys, no modification of the IAT. Just a quick little overwrite. And they took advantage of the fact that Windows page aligns and uses that page alignment from the disk. So it's a problem, and we're seeing it in malware a little bit. So that's the story of why we don't do section fix-up, things like that. We sort of try to take the most virgin look we can at the actual binary. So we got to a point where we had this solution, but the file size for binary that you acquire in memory is going to be different from that you acquire on disk, or from that's on disk. So we used bindiff to compare what's in memory to what's on disk, and we were able to verify that our approach was successful and that we were acquiring the right amount of binary. We weren't messing it up. So that was how we verified that what we were doing was correct. So real quick, I'm just going to say, tying it all together, scan the kernel memory looking for all processes, parse the memory sections for each process, dump each memory section to a separate file on disk. Pretty simple stuff when you think about it. So what are the benefits? The benefits are quite numerous. By parsing physical memory and not doing the virtual address stuff and having access to live physical memory, we can dump all the executables, DLLs, stacks, heaps, everything that can be useful in reconstructing what might have happened with that process. We also can bypass any anti-debugging techniques. We're not attaching. The process has no clue that we're touching physical memory. So it's pretty safe to say that you're gonna have to actually look for our process name and kill us off and have pretty process-specific attacks to subvert us. Recently, Dave Vitale released a rootkit that used debug registers or trap referencing to hide a virtual address range. Because we don't access virtual addresses, we go virtual address to physical memory, and we don't ever read from the virtual address. We only read from physical memory. This type of rootkit doesn't work on us, and that's a good point to make. The other thing is, if you have an injected DLL that's only on disk, for example, Metasploit has something called Meterpreter that loads a DLL off the wire into memory without ever putting it on disk. It patches the load library, I believe. we acquire that DLL intact with the import address table, and I'll actually show you that, hopefully, time permitting. Finally, we acquire code corresponding to injected threads, and we'll acquire shellcode if it's still in the stack and heap, which will allow for analysis later. So we got this process acquisition working, and it's cool, but what can you do with it once you have it? Once you've acquired the process on disk, obviously you can stick it in IDA, which is what most people are going to do. But let's take it a step further. Let's come up with something that's a little cooler. So I wrote this tool called Find Executable Code. It's a prototype, which means it's not being released here. It's still got some bugs and some fix-up things that need to occur. But basically, the goal is to successfully, and some of you, for who you guys work for, may have thought about this problem. We want to successfully identify shellcode in memory, injected DLLs in memory, and injected threads in memory. And we want to be able to do it on shellcode that's 9 instructions small. Size shouldn't be, our algorithm should be independent size. We need a successful way to do this. And a lot of people have tried to, and we think we've come up with a solution for it. Basically, one of the biggest problem you have is that you need to be able to differentiate garbage in memory that translate to valid instruction, that translate to valid x86 from injected x86. So you need to make sense of what you're reading and say, well, this sequence translates correctly, but it doesn't make sense. And that's the problem most people run into. So I'm going to tell you how we do it. Our algorithm consists of breaking up the file. We work on a flat file. We don't work on live memory. So hypothetically, Word docs, things like that, this algorithm will work. You break the file up into 256-byte chunks. We take that chunk. We do entropy analysis. We say, in tests we found that entropy value of 3.5 or greater is a great indicator that there's x86 instructions. We may find all these values are highly configurable. This is what we found in real-world cases, and we're only using real-world cases. We're really not developing our own solutions to prove our theory. We're trying to take malware we find on customers' computers and determine that, hey, this tool still works. So we say 3.5 is the entropy. Once that passes that check, we then say we found that there are a lot of strings in memory. You've got your environmental block on the heap that has a lot of strings that'll throw entropy way off. So we do a string ratio. We say if the percentage is greater than 50%, that there's a contiguous 128-byte string, either Unicode or ASCII, we discard it. And I'll take a moment here to stop and say, if you use ASCII shellcode encoding, what will happen is we'll have our 256 bytes will be a complete string, and I'll have 100% disassembly ratio to that string. And that's a perfect indicator that I've got ASCII shellcode on my stack or heap. So the ASCII factor that we discard, there is a check to figure out that we're not discarding actual x86 code. We then use our own disassembler called NickDasm. The name is subject to change, and it's named after the person who wrote it, Nick Harbour. And this ensures low false positives. What this disassembler does is it says from offset 0, disassemble. Then from offset 1, disassemble. From offset 2, we brute force disassemble, and then we pick the best disassembly. In some cases, there's no valid disassembly, and we discard the 256 bytes. If there is, we then continue with that disassembly. The final two algorithms we use, one is called PPMJXC, which stands for push, pop, move, jump, XOR, and call. Basically, the instruction ratio should be a push. There should be a high instruction ratio for push, pop, move, jump, XOR, and call. What we found in the real world is that, yes, without people knowing our algorithm and specific attacks, this proved true, that the shellcode, the injected threads were of this type and were a very high ratio. And the ratio is configurable. And finally, the one thing that x86 has to have is an ending signature or a control flow transfer. That is, there has to be a call at the end, there has to be a jump at the end, there has to be a return. It can't just keep going off into garbage memory. What this means is that our algorithm is going to be able to find the ending parts of shellcode, injected threads, and big portions of DLLs. So you're guaranteed to find a little part of it, and then if you do further analysis, you'll find the rest of the code above or below it. We have a 100% success rate in finding injected DLLs. Basically, injecting a DLL, there's too much code in memory for us to miss. We have a great success rate in finding shellcode and injected threads. I'm going to show you now, first demo, which is actually a malware that was found on a customer's computer. Can everyone see this? All right. What we have here is the process address space has been acquired. We have the DLLs in red. Known DLLs are in red, and executables. We then ran this, and the reason I didn't run this live for you is one of the problems is the runtime of this thing is very long, so we would have been sitting here for a while. So I pre-ran this. The green here indicates that we have possible x86 instructions that we consider valid. So if we go and disassemble it, first off, this is 9 instructions that we found out of the process address space successfully with no false positives. And we actually did reverse the malware to determine that this was what it was doing. So we know that this is valid. Basically, your get EIP commands are right here. They then figure out that there's a string. They push a flag, then they push the string, then they call winexec. And I'll just show you that it's an idle right here. And if we look right here, there's putting a command shell into Notepad in this case. So that is how successful we can be in finding such a small set of instructions. And really, you're not going to find a real-world instruction set that's much smaller than 9 instructions. Shellcode, the smallest you may find, Win shellcode, maybe 128 bytes, 256 bytes. So this is a pretty good indicator of the success we may have. All right, so that was find executable code. The tool that's being released in the URL that's right there that you guys can grab up is Memorize. It does more than just process acquisition. I'm just going to tell you really quickly what it does so I can get to my demos so that I can get you questions and stuff. It's going to acquire, it can do memory dumping. It can list loaded drivers. It can enumerate processes. Within the process enumeration, it can enumerate the handle table. You can see the files, things like that it has open. Enumerate memory sections, enumerate open ports. We understand how ports look in memory. We don't rely on no API calls for all this. We do the parsing ourselves. We understand the kernel structures. We use strings in memory, which is a very revealing thing if you look at strings in memory for malware. We can acquire processes, and we can acquire drivers. So if you have a rootkit that's hiding itself on disk, and you don't want to bother unhooking it, just acquire it, and you'll get it in memory. We can detect hooks, and we use the page file when we're running on live memory. So that's a quick little blurb about Memorize. So the conclusion, the state of process acquisition was good, but wasn't great. We now have a way to acquire a complete process address space. There's still plenty of room for improvement. I'd like to implement my own IAT reconstruction for both drivers and user-land processes, which is a little different from what I've seen with the Windows driver loader and the Windows PE loader. There appear to be some caveats. I want to improve our executable code identification to the point where we can run it in a real time. We want to parse files that are backed by themselves. Better post-process acquisition techniques. More stuff like find executable code. Maybe better string analysis, things like that. And the thing that we're saying now is that memory analysis in the forensic world and malware analysis are completely mutual. They have a lot of things in common. Both fields want to do. So it's good to keep that in mind. So feel free to download the tool, use it, and now it's time for demos. What I will say is I've pre-done a bunch of the running stuff that may take some time. I had about 20 minutes to demo. I only have 20 minutes of time left, and I want to get you guys to time for questions. So I may cut something short here. But demos, and if you have any questions or you want to ask me stuff further and you don't feel comfortable now, you want to see find executable code run on something else, feel free to stop me. I'll be here today and tomorrow, so I can answer those questions. All right, so all right, this is better. So when you install Memorize, you get these files. The batch files, I'm going to try to go through this quickly because I do know how much time I need and how much time I have. The batch files will actually execute Memorize, or you can execute Memorize from the command line. You have to configure your XML files. So this XML file, it has the following. This is our memory acquisition. I'll show you this one. This is the actual full process acquisition audit. You can specify a PID right here, or the process name. Either one will work. And we can pull it out of a memory dump, so it doesn't need to be on live memory, which is a pretty nice thing, especially if you're doing forensics. So that's the acquire process, which is what we'll use. I'm going to do a demo here. I pulled this sample. Oh, I guess. Forgot a slide. The demo that I'm going to be doing here, the first one, is going to be here. We have a Themida packed binary, and Arrow is going to be talking about Themida and some other really cool packers in the next section, so I encourage you to stay. The binary, we're going to run Ollie debug first, then run the malware. We're going to see what happens. We're going to run the malware, then run Ollie, see what happens. And then we're going to acquire it because we can't acquire it using our traditional methods. And then I've already run the find executable code on Themida to discover some interesting things about Themida. So I'm running Ollie debug. This is the file. I got it off of offensive computing. I run it. It pops up a warning saying it's not going to execute because it already knows that there's a debugger running, which is pretty neat. All right, well, let's try to trick it and just kill Ida or kill Ollie real quick. I'm going to infect the machine now. Networking's disabled, and so is my host machine networking. So if you have any fears, do not. So we see it. It's doing a bunch of stuff here. And this is the actual lsas.exe. I was going to show you that lsas.exe is a Themida-packed binary. I was going to show you the difference in, actually, we'll try to do that real quick, actually. So lsas.exe exists at Windows System 32. So this is the file on disk. I'm not going to really let it finish analysis, but it's got two functions which are pretty unuseful to us. If we look at the strings, it's really not going to have anything that's useful to us. As a malware analyst, we have no clue what this binary is doing. We do know it's running in memory, and that's bad. So let's go back to our VM real quick. Let's run Ollie now. Let's just keep an eye on LSAS. We're running Ollie. Let's go to attach. It's found Ollie's running in memory and just killed itself. So you can't even get Ollie up. If you did this with Windowbug, it doesn't kill itself on. It will just kill it when it tries to attach. So let's reinfect ourselves real quick. We'll wait for lsas.exe to finish running. We'll do process dd bat. You have a bunch of different command line options. I'm going to use the PID one. I want to acquire 1056. It's going to drop the files in this audits directory right here. Real quick, I'll draw your attention to a couple things. We determined from memory the major version of the operating system right there. And from memory, we also determine the minor version. So from both, we do it from memory, no API calls. We're able to determine both. And it's already acquired the process address space. So this is what the address space looked like for this binary. We've got, it's still acquiring, hold on. Okay, so here are all the DLLs that it had loaded. Here's the actual binary itself. We have our stacks and our heaps. So let's, I'm just going to, this was the LSAS on disk. Let's so it's going to be loading it up. I'm going to need to hit a couple buttons here. This acquired binary has 514 functions, so we know we've got it in a semi-unpacked state. Arrow's going to talk more about Themida, but real quick, Themida is a function-level encoder, so we know that we don't have a full look at it, but we have a good part, and a determined reverse engineer may be able to make sense of what's going on, partially. So it's going to do analysis. Oh, it's done. I'm going to run this real quick. I can show you some strings. While I'm doing that, I'm going to jump back into the VM real quick. I'm going to run another audit. This audit tells me about the process itself. I want to know its handles, its strings, its ports, stuff that I may not be able to get when I reverse, just any metadata that may help me and speed up the malware analysis process. So I'm going to turn on handles. I'm going to turn on sections. I'm going to turn on ports. And I'm going to turn on strings. This is going to run the memorize with these options. I've actually already run this audit and saved it so I can show it to you so we don't have to waste time. The end result here is this XML file. Basically, you have your metadata, the username. All of this is taken from memory, the times, the path, the name of the file. You have a string list here. And analysis of the string list can tell you a lot about a binary. So we have a DLL. No, that's not it. So we have a DLL VM6 DLL. And we also, above that, have a couple very interesting strings. Themida string, pstore EC string. And if we scroll down a little further, we have a compiled string here. And here's a string that may tell us what this actual Trojan is, since it's unnamed at this time. This string, very interesting. So that's what you can do from just process memory analysis. We're able to pull strings, and the IDA should be able to pull out some of that as well. So these are the interesting aspects of Memorize. Besides the process acquisition, once you acquire the process, you may need metadata because you may not be able to get a good snapshot of it. The import table here is completely wiped out, and we don't do any fix-ups, so it takes some manual work to get the import address table working. But the one thing I'll show you is that this is something we'll be releasing as well. Instead of having to look at an Internet Explorer doesn't handle big files really well. So this is a tool. Basically, it parses the XML file. These are the files that the process had open at the time. Directories had no process handles. These are the registry keys it had open. Mutants, DLLs, it had loaded. The strings that we already saw, memory sections, and it had no ports. So real quick, I know I'm going fast, but it also, this is the Themida process in find executable code. We see it has some x86 code. I believe these are false positives, actually. But this cyan color right here are injected DLLs. These are 3 injected DLLs that, when you reverse out, will actually show you will actually be legitimate DLLs. So that's the first demo I wanted to get to. The second demo is this. Basically, we acquire what happens in a forensic example where you want to use this tool forensically. You have a process that's been exploited, or you believe it's been exploited. Your hint may be the port it's listening on. You acquire that process, or you take a memory dump. Then you acquire the process out of the memory dump later on. You identify what process you believe has been exploited because you're able to see that the attacker used the default Metasploit port, for example, which would be 4444. Once you've acquired the entire process, you can now find the shellcode and any injected DLLs of Metasploit. So let's actually show you this. So this is SVC host. It was exploited using Metasploit. It was a Service Pack 1 box, so obviously there's a number of exploits that could have been used on it. The red, again, is just known executables that we don't analyze. Green is the believed shellcode. That one you see right there is actually a false positive. But what we have here is the one we're looking at here, which is memory section 11D0, which is right here. We believe there's shellcode on it, and if we see here, if we disassemble it, we have a pretty good idea that this is definitely valid x86 instructions. My theory about what this, I guess, yeah, you can see a little bit better up there. Basically, this is probably a portion of the metinterpreter loader. We're able to identify it. What this means to an analyst is that, all right, the process has been exploited. I've identified part of it. What I do from here is, because we look for ending signatures, there may be information above. There may be this section right here may contain more of the function. The section below may contain another function, and it actually does, I believe, here. Another more valid x86. So we scanned the SVC host, which has a ton of threads and a huge process address space usage. We got one false positive. The second hit is valid as well. I'm not going to take the time to show you because I'm running short here. The one thing I want to show you as the final thing is it found 3 injected DLLs. 1, 2, 3. What I'll do here is this is the memory section. If we look, it's got the base address. And if we go back here, Same base address. Everyone sees that? Just so you guys know. I'm going to overwrite it just so you guys see that I'm not playing any tricks here. We'll just reanalyze the binary real quick. It's done. The import address table on this binary is actually intact. This binary, and I can confirm this binary is actually the interpreter binary itself. So we found not only the shellcode, but the injected binary. This binary is not on disk. It's only in memory. So no traditional disk forensic would actually ever see this. One way to show you just further, there's the metaserver DLL. That's just the name it uses when it loads itself. It's not loading off disk. So we've been able to prove that we can find shellcode in memory, we can find injected DLLs in memory. And if you want to just look at this file and hex edit real quick, you've got your MZ header, your PE header, and this was all taken from memory, which is a pretty nice view. So that's that demo. I want to thank Dylan and Hack in the Box for having me, and I'd like to verbally thank Ken Bowen, Jamie Butler, Arrow, Nick Harbor, and Peter V. And now I got about, I think I got about 9 minutes for questions, so open up the floor if you have any. Hopefully you do, otherwise you can do another demo. Anyone? No questions? All right, then I'll cut it short. Thank you guys very much.
Thank you very much, Mr. Peter Silberman.